Alright, hey everyone, so this is Lab 9, Soluble and Insoluble Salts. Sorry I'm a little bit late getting this in today, I had to work late. But before we get started, I want to show y'all exactly what you need to do for this lab. And then we'll get into the pre-lab discussion and everything just in case. Because I think some people's been missing this. And I don't want to confuse anyone. Okay, so and when you open up your PowerPoints and you start your virtual lab, the omissions section is what you don't do. Okay, so we are leaving off procedures B and D, and from the report sheets, Part D, or excuse me, Part B, all of page 107 and page 108, Part D and Q5. So go ahead and go into your lab manual and mark those parts off. You don't have to do those. So I'm going to show you on the lab manual which parts to mark off. Okay, so they said Part B, so you can mark off all of the solubility of potassium nitrate. Part D, the purification of water, so you can mark all that off. And then you're going to also mark off those parts on your procedures, right, to make sure you're not worrying about that. So all of Part B and then all of Part D. Okay, the only part you're concerned about on this page is Part C, testing the hardness of water. And then pre-lab questions you don't have to turn in. Now these are for you to keep. If you want to ask questions about them or you want to know what the answers are, you can email me and I can send you whichever problem you're working on. But you don't have to turn those in. Okay? So keep coming down. We're going to mark off Part B from the report sheet as well. So solubility of KNO3. All of this gets marked off. You're not doing any of that. And then right here at Part D and question 5, mark off those. So that's the omissions. Those are the ones you don't do. Okay? So just wanted to clarify that. I think some people have been missing that because I've been getting extra answers, right? More answers than I require on the report sheets. So just know that omissions means leave it off. Don't do it. Okay? Omit it. Omit is to leave out. All right? So, with that being said, let's get into what we're going to be doing in lab today. So, we've been talking about, in your lecture and my lecture, we've been talking about solubility solutions, right? So, let's touch on a few of those real quick before we actually jump into the lab. Okay, so first off, we need to kind of review a couple of things. We talked about solutions, right? Solutions are a homogeneous mixture, meaning they all look the same. There's not some solid particles and some water particles or whatever in there. Okay, so this is just a cup of water or something, very ugly cup of water that doesn't seem to be showing up on your screen. Give it just a second. Come on. Pick it up, pick it up. Let's go. Why would it be freezing like that? Let me see. Oh, come on. Okay, something about the location that I have it at. Let me see if I can't move it a little tighter and keep this thing working right. Okay, so you may lose me right here for a second. I'm going to try to get closer so that this thing always picks up. Let me see if I actually can turn this a little. Okay, so we said still doing it. This is a cup of water, and in this I have a solution. All right, now a solution is a homogeneous mixture, meaning I can't see the difference between anything that's in there. Some examples of solutions would be like salt water or a cup of iced tea, right? Or excuse me, not iced tea, no ice in there, just sweet tea. It has sugar, it has tea, it has water, so it has all these different compounds in there. But if I look at it, it all looks the same. I can't tell the difference between the water, the sugar, and the tea, right? So this is what we call a solution. It is a homogeneous mixture, meaning it all looks the same, and it contains, typically it contains ions and other chemicals in there that dissolve in water. Okay, and so that's why we say a solution, because it dissolves and becomes a solvent and a solute. Okay, so the whatever you have the most of is the solvent. Usually it's water. So in the case of tea, the sugar is a solute, right? Let me spell this out. The sugar is a solute. So, and then the tea would be a solute as well. Now, the solvent is whatever you dissolve the tea and the sugar in. So, that would be water, right? In other cases, it might be something else, but usually it's water, especially when you're dealing with non-polar molecules, or excuse me, polar molecules like ions and salts. Okay, so let's go to that. Salts. A salt is anything that combines two ions. Remember, ions is something that exhibits a charge when it's in solution. Okay, so a good rule of thumb that I like to keep up with is just pay attention to which side of the periodic table it's on. Okay, so everything under sodium, which is in group 1, typically breaks down in solution and becomes a positively charged ion. Everything under the chlorine group, the halogens, so bromine, iodine, chlorine, for the most part, will break down in solution and become a negative anion. Okay, so these combined are what we call salts. Salts are any ion pair, um, really essentially any ion pair. Now, when it's in water, what you'll see is water has little charges around, little positive charges around the H. So let me circle that, see if you can see that, and a little negative charge, partial negative charge we call it, around the O. Okay, remember the opposites attract. So what happens is when I dump salt into water, NaCl, these ions will split up and they'll attract to the opposite charge of the water, or the water will attract to it. And so what ends up happening is water surrounds the sodium individually, and it also surrounds the this should be an H, the chlorine individually. Okay, so this, it'll pop up in just a second. HH plus, that's a plus, that's a minus, it's a plus, minus, minus. Okay, come on. I've got all these charges circled and they're not wanting to catch up. Come on, boo. Here we go. Oh no, come on. All right. I mean, it still hadn't caught up all the way. But what you'll see is that the charges attract to each other and water ends up encircling all of these different ions and it spreads it out. So a solution is equally distributed in that way, right? I have the same number, there they finally get caught up. So you see these little circles are the charges around each atom. And I'll just put them there to illustrate that they have attraction to each other. Okay, they pull on the chlorine molecule, the water pulls on the chlorine and it separates it from the sodium, the Na, and kind of surrounds each one individually. And so when you put salt into water, it dissolves and breaks up, water surrounds it all, and that's how it equally distributes amongst the water. That's why if you taste any bit of that salt water, it all has the same saltiness because that salt has been distributed all throughout the water. The reason it distributes like that evenly is because of the charges around water and around the ions, sodium and chloride. So this is a typical thing that happens in solutions. Solutions are usually contain ions, and they're ions because they dissolve and they form a charged particle in water. Okay? So now that we've covered that, let's talk about the chemical equations. Just very simply, I could say that NaCl plus H2O will yield, and I can put a little, let's actually take that away. I want to put a little L there. So I'm going to talk about all this that I'm doing here. Na plus Cl minus plus H2O. Okay, and then I can come in here, put a little AQ here, and back to a L again there. Okay, so now this is a very simple equation. It's not actually showing any reaction. It's just showing that sodium chloride, when I had it as a table salt, it was a solid. That's what this S means behind it. I mixed it with water, a liquid. That's what that L means behind it. And then the sodium and the chloride dissolved in water and became aqueous. That's what this little AQ stands for behind each one. So kind of keep up with all this. This is how we indicate what form that the atoms are in. Okay, and remember, it can be a solid. If I don't have it in water, once I dissolve it, it becomes aqueous. Water is always L, so unless it's a gas and I'm right, like I'm burning off steam, cooking off steam or something, it could be a gas, but typically it's a liquid, and so we'll use L behind that. You don't have to use AQ for water because everything that is AQ is dissolved in water. Okay, so this is showing that I've created charged ions by dissolving them in water. Okay, that plus and that minus for the NaCl. It's showing the ion pair, essentially. The NaCl, the Na gives up an electron, becomes more positive. The chlorine accepts that electron, becomes more negative. And they stay essentially separated in water because of what we just talked about. The water gets in between them, pushes them apart or whatever. So this is what we call an ionic equation, okay? And when I say ionic equation, it says essentially that I'm illustrating these charges, okay? And we've talked about these charges. Those charges typically come from the periodic table. Waiting on these arrows to catch up. Yeah, the charges, okay? We get these charges from the periodic table. So NaCl, let's go take a look at a periodic table real quick. So Na is in group 1, right? Over here on the left. Make sure y'all can see what I'm saying. Yep, group 1 over here on the left. So remember, whatever group it in, that's how many valence electrons it has. And we said that we set 2 end zones. Either I want to have 0 valence electrons or I want to have 8 valence electrons. So everything on the left side of your periodic table is going to probably try to get to 0. Okay? Everything on the right side of the table is going to try to get to 8. This what we call a noble gas configuration on this far right side, group 8. All these are noble gases. And they're the most stable because they filled that outer electron shell and they're very stable and they want to stay that way. It's very hard to mess with them. You can't react them. You can't mix them. They're what we call inert gases. They're not easy to deal with. So all of these other atoms, the fluorine, chlorine, bromine, they're trying to get to that noble gas configuration. I'm over here in group 7, the halogens. So what they will do is accept 1 electron and become negatively charged by 1 and fill that valence shell with 8 electrons. The oxygen will take up 2 electrons to get over here to group 8. The sulfur will do the same thing. It'll take up 2 electrons to get over here to the argon configuration. On the left side, what they do instead is they give away electrons so that they can get to 0 on the outer shell. The hydrogen will give 1 away and become what we call just a proton, just a positive charge with nothing else in there, right? The lithium gives away 1 electron, becomes lithium positive 1. Beryllium will give away 2. Magnesium will give away 2. Calcium will give away 2, and they'll all be 2 plus. Okay, so that's the trend. That's how you know what the original charge is. And then when you go to do your ion pairs, you just have to make sure that you match the charges. Okay, so now that we've talked about that, let's look at the lab for today, and let's kind of put all this into action. All right, where is the lab? So I posted the lab manual on Cougar View. I've left off the page 107, which you weren't responsible for, so don't worry about that. If you notice that you're missing a page, that's expected because you're not doing anything on page 107. Now, another thing I've done is you have this table here, and we'll get back to this in just a second, but I've actually given you a better table. So let me show you that real quick. Where's that? Solubility rules, okay? So if you open this up, you might need to expand it, maybe blow it up a little bit. How do I do that? No, don't do that. Okay, this is about as big as I'm gonna make it. Oh, y'all can't even see that. Hold on. I'll just leave this here. Okay, so what you'll notice here is I have, remember those polyatomic ions that we talked about? They're like their own little thing, the SO4, CO3, PO4, OH is called hydroxide, S is a sulfide or sulfide. Yeah, so just remember the polyatomic ions are their own thing. All right, and you see a couple of those here. Nitrate is NO3, it's up top. Now these also have charges associated with them. You can't see them as easily here, but when you open up your own table, kind of blow it up and make sure that you can see this because you need to be able to match these charges. But I'm going to read them off for you right here just so you know. NO3 has a 1 minus charge. Acetate, which is C2H3O2, has a 1 minus charge. Chlorine, bromine, and iodine all have 1 minus charges. Sulfate has a 2 minus charge. Carbonate and phosphate carbonate has a 2 minus charge. Phosphate has a 3 minus charge. Hydroxide 1 minus. Sulfide 2 minus. Sodium, potassium, and ammonium all have 1 plus charge. Okay, so it's important to keep up with that. This table I think is better than the one that's in your lab manual, but both of them can be used. Okay, now how do you use them? Go back to the lab manual so I can kind of walk you through this. All right, so we said that ions form in solution. I dump salt into water, it splits up, becomes NaCl. Now there are cases where if I mix two ions, they'll group up and they'll form an insoluble salt, and they'll start to fall out of solution. So imagine if I mixed salt and say something else, but I put it in the water, and then all of a sudden I see granules start to fall out. And I might think it's salt, NaCl, but I know that salt dissolves in water, so it shouldn't be salt. Well, in fact, what's happening is we're actually seeing a chemical reaction. Okay, so let me go to this first example, will be fine. AgNO3 plus NaCl yields AgCl plus NaNO3. Okay, so I'm going to bring you back to my iPad and I want to write all of this out, and I'm going to break it down how you're going to need to break it down. So what we're going to do is we're going to write, let me pull my manual over here just so I can say this without having to go back and forth. Okay, so what we're going to do is we're going to write the chemical equation that's happening. Okay, there's a chemical reaction here happening. We're actually forming a precipitate. So in the other lab, you got to see this. Remember, anything that got cloudy or fell out of solution was a precipitate. So that's what's happening here today. You're going to watch some videos and you're going to see some examples of these reactions, okay? These combinations of different ions and then they'll group up together. Some of them are soluble, meaning they all dissolve in water. Some of them are insoluble, meaning they'll form a solid and will fall out of solution down to the bottom, and you'll have water with some ions in there on top of something solid that has fallen to the bottom. Okay, those are called insoluble salts. And that's what that chart kind of leads you to. It shows you how to distinguish which salt was insoluble. Okay, and that's the point of today's lab. So first thing we're going to do is we're going to look at this example they have here. This is actually one of your problems, I believe. Let me scroll down here. So if you're doing your work on the while we go, AgNO3 plus NaCl. Is that what I'm mixing here together? AgNO3 plus NaCl. So this is exactly like the first part of the problem. So I'll go ahead and work through this with y'all. This is the first part of the first section of part A. Okay, and you'll have to do, like I said, an ionic equation and a net ionic equation. Here are examples of all of that, but I want to work through that with you right here. Okay, so our equation is AgNO3 aqueous plus NaCl. We'll say solid just because. I don't think they use solid on the thing. Let me see what they use on the text. NaCl aqueous. Okay. I'll change that. AQ. Can y'all see that? Okay. And then I'm going to put my little yield sign. Now remember, my board, you'd like to do all this in one row. I have a limited amount of space here. Okay, yields. And now this is when I'll go to my table and I'll try to figure out. Now we've looked at reactions, right? There's single displacement and double displacement. Okay, when I have essentially 4 ions here, right? 1, 2, 3, 4. I can assume that it's going to do a double replacement. Okay, so let me take off all these circles. So what I'm going to do first is I'm just going to switch them. Okay, Ag will switch and go with, remember Ag is a plus. Now this is why I say it's important to look at that table and see what your charges is. I know that nitrate is a -1 charge right here. Okay, in order for that to be paired up with silver or gold, I think that silver. With silver, then that silver has to be +1. Okay, I think I kind of jumped ahead of myself there. I know that sodium is +1, and I know that chloride is -1. We just established that, right? Group 1, they tend to give up 1 and become a positive. Group 7, which chlorine's in, takes up 1 and becomes negative. Okay, so these equations are going to be balanced, meaning that, let me make sure that they're all going to be balanced. Not necessarily. They're not necessarily going to be balanced. So you're going to need to balance them. How do you balance them? Well, just match up the charges. You want the same amount of positive charge as you do negative charge when you hook up the 2 different ions. Okay, so it's really just that easy. The Ag is a plus, so it's going to hook up with the negative chlorine. I circled it. Come on. Come on. There you go. Okay, so that the positive Ag is going to hook up with the chlorine and make AgCl. And then the nitrate is going to hook up with the sodium. Always list the metal first, so sodium first, then nitrate. Now, and I'm actually going to erase this S because I already know what that was, and your book will tell you too. But now we need to figure out which one of these, the AgCl, come on, catch up, or the NaNO3, which one, there it goes, the AgCl or the NaO3, which one of these are insoluble. Now I'm going to go to my table. Let's use the one that I gave y'all. No. Solubility. Okay, so nitrate. It says all nitrates are soluble, no matter what. So what does that mean? That means that this NaNO3 right here is definitely soluble. So I'm going to go ahead and break that up into Na plus NO3. And I'm going to put that AQ because that's what soluble means, right? Aqueous. It's little AQs down there, AQ plus AQ. And the NO3 has a negative charge on it, so that's what that is right there. I'm going to erase these little underlines so that you don't get confused. That's a charge. Okay? And I'm also going to circle the charges. That looks a little prettier. That AQ does not look pretty. That's an AQ. Yeah, okay. So I'm actually going to erase that because we knew that that's not the solid. Now let's check and make sure that AgCl is the insoluble salt. So I'm going to go back to that table and I'm going to look for either Ag or Cl on the table. So it says Cl right here, ion Cl. All chlorides, bromides, and iodides are soluble except when they're paired with silver, lead, and mercury. Okay? And it talks about lead a little bit. But so Ag, when it's paired with Ag, it is insoluble. So that's my solid. And that's why I'm going to write AgCl solid plus NaAQ plus NO3 AQ. Okay? So now this is the standard equation. I didn't have to balance anything because my charges match. So that makes that easy. Now I want to break it down into an ionic equation. Okay? So what does that mean? That means I'm going to make all of these original ones, AEG, NO3, and NaCl, I'm going to break it down into ions in the beginning. And everything's going to be in terms of the plus and minus charges or the ions. Okay? So Ag plus NaQ. And you want to put this behind every single atom, okay? Unless it's a molecule like the AgCl will be, because it's a solid and it's a combination of both. The aqueous, the AQ behind it just says this is dissolved in water. It is not insoluble. Insoluble is when it's going to have the solid. Okay, so Ag plus NO3 minus... let me circle my charges too, just so you don't get confused. Plus Na plus Cl minus yields all of this on the left side. Come on, catch up. There it goes. Almost have to get right on top of the router. So weird. Okay. And then on the right up, I gotta add my AQs. I didn't do that. AQ, AQ, AQ. Okay. All of this is very important. Now I can do my right side. AgCl solid, right? My table said that the AgCl is a solid plus Na plus AQ plus Cl minus AQ. Okay, so I kind of got bunched there at the end, but I think everybody can see that. Okay, so this is the total ionic equation. Now, when I want to find out what the net ionic equation, I'm going to go through and mark out everything that is the exact same on the left as it is on the right. Okay? So, which one of these ions is the exact same? It doesn't change from the left side to the right side. Well, let's see. I didn't write this out right. Sorry. Hold on, let me back up. This should be a nitrate, not a Cl, because I hooked the Cl up with the silver. NO3 minus and AQ down there. Okay, so now, net ionic equation. Mark out everything that's the exact same on the left side as it is on the right. So nitrate is the same on the left, same on the right. Mark both of those out. Sodium is the same on the left as it is on the right, so I'll mark both of those out. Ag, silver, joins up with chlorine, so that's not the same. It's positively charged on the left side. There's no charge on the right side. Remember, anything that's a solid, liquid, or gas has no charge. Okay, so the chloride also changes charge. It's negative on the left side, but when I hook it up with the silver, they share those electrons in what's called a covalent bond, and it's no longer negatively charged. They share it and they're balanced. Okay, so there's no charge. My net ionic equation is going to be Ag plus Aq. My A and my Q looks very similar. Aq plus Cl minus Aq yields AgCl solid. Okay, and that's my total net ionic equation. Now I want to do one more where, oh, sorry, hold on just a second. I want to do one more where we might need to balance something. So let me look at that. I'm actually just going to go ahead and skip down to the very next one. It's silver nitrate plus sodium sulfate. Okay, just to show you where I'm at. Where's the book at? I'm right here on this table, silver nitrate plus sodium sulfate. Okay, and so the first one that we did is all of this, the ionic equation and the net ionic equation. Now we're going to do silver nitrate. I'm going to write this down. Silver nitrate plus sodium sulfate. Okay, and I'm going to leave off all of that other stuff till I can show you what I'm doing. Okay, so here's my problem. Now I'm going to do this. First thing I'm going to do is I'm going to go through and assign charges, right? So we did Ag the last time. We know that that's a plus. Now I'm going to leave it here, but I'm going to go through and write the charges above it so that I know when I break it down how that's going to go. So sulfate, I'll know from my polyatomic list, is 2 minus, and 2 sodiums together are 2 plus, but individually they're 1. So each sodium brings a plus 1 charge, making a total of 2 plus right there. So now this creates an interesting problem. I can't straight up displace Ag with SO4 because they don't balance. I have a plus over here, I have a 2 minus over here. So how do I balance it? Well, let's start by doubling this, okay? Let's say I double the AgNO3 with a coefficient, right? So I'm going to rewrite all of this with that coefficient in there and then try to balance. 2AgNO3. Remember, if it's a coefficient, that means everything behind it. There's 2 of everything behind it. I'm going to put my little AQs in there now. Plus Na2SO4. Na2SO4. Okay, and I'll put a little AQ there. Now that yields, now I need to go to my table and figure out which one's soluble or insoluble. So let's go to that. I'm going to use the other table in your lab manual this time, so it's in case you want to use that, you'll know how to use it. Okay, so if it's soluble, if it contains any of these, it does contain sulfate and nitrate. Okay, so it's soluble if it contains nitrate, period. That means nitrate's going to be one of those ones that doesn't do anything because it's always soluble. So the other one is sulfate is soluble except when it is combined with barium, lead, calcium, or strontium. So I'm not combining with any one of those. This actually looks like both of these are insoluble. Let me check the other table I gave y'all just to make sure, but it looks like neither one of these is going to make an insoluble salt, right? Because sulfate only makes an insoluble salt when it's combined with those four cations, and I have none of those here. And then nitrate doesn't ever make an insoluble salt, so I'm guessing that there's no reaction here, and that's what I'm going to write. Let me bring y'all back to here. All right. So first I'll just go ahead and switch it just for, the heck of it. So let's switch out. It'll be Ag, 2Ag plus SO4 plus 2Na plus NO3. Okay? Now, the reason I split all of these up is because none of these are soluble. Now, you'll notice that instead of putting the 2 behind the sodium this time, I put it in front because when I break that down, they are individual now. When it was behind the sodium, when the 2 was behind the sodium, it was implying that it was a part of that one molecule. But when I put it as a coefficient, it's saying there's 2 individual sodiums. And when I break it up in water, dissolve it in water, that's what happens. The water gets in between the sulfate and the 2 sodiums, and it spreads them all apart. Okay? So now that I know there's no reaction, let's go through and do the ionic equation. Okay? So it is 2Ag plus AQ plus 2NO3 AQ plus 2Na plus AQ plus sulfate AQ 2 minus. I'm going to circle all the charges so that you don't get confused. Bop, bop, bop. There goes that, and it actually yields the exact same thing. 2Ag plus AQ plus 2NO3. And honestly, you wouldn't, since there is no reaction, you wouldn't have to put all the 2's because I don't actually have to balance. But it is a good practice just to keep doing it. Where am I at? Plus 2Na AQ plus sulfate 2 minus AQ. Alright, so now if I go through and mark out all the things that are exactly the same, I'm going to end up marking out the whole page, and I'll put under net ionic equation, I'll say no reaction. Okay? So, that's good for that. Now, how am I going to post the videos? I guess I need to let y'all actually watch the video. I'm going to play the video for y'all on the PowerPoint because I had a lot of people say that, it didn't work for them last time. So I'm just going to play it for y'all directly. Okay, so let's try that, and hopefully that'll be the best way to not have anybody miss their video. Okay. So I'm back at the PowerPoint. Let me make sure y'all can see this. Okay, so yeah, go through your PowerPoint. Make sure that you're ready. Actually, you know what I'll do? I will post another video right after this one where I play each individual video because I don't want to go through trying to decide. Yeah, I don't want to really talk while y'all watch the video. So that's what I'm going to do. I'm going to post another video where I just play each one of these individually. So look for lab videos. This will be PreLab Discussion, right? I'll post this as a PreLab Discussion, and then I'll do another one called Lab Videos, where I'm essentially just going to start playing this, and that'll let y'all watch it without having to have the movie file or MP4 or all the other problems that I had last week doing this. So that's it for today. This is not due till next Sunday. So yeah, let me know if you have any questions about this, and I'll be around all weekend, so y'all just email me and let me know where you're at. I did catch up all the grades up to lab 6, so all your midterms should be done in all 5 labs if you've turned them in. If I don't have a grade for one of those labs, and you should have one, let me know, and I might need to try to find it, like especially if you emailed it to me or put it in my Dropbox or something. So that's it. Like I said, look for this video. I'm going to post another one where I play all of the different lab videos directly for you. So that's it for today, this weekend. I will see y'all next week. Bye.